first example we want to look at is just using some function algebra to remind us of some of the algebraic properties when doing function algebra. So use f of x equals 0.0001x squared plus 3 and g of x equals the square root of 120 minus x to answer the following questions. So write the formula for h of x, where h of x is equal to f divided by g. So this tells us then that what we really want to do is just divide f by g. Well, we know what f is, and we know what g is. So we are going to just evaluate our formula at those values. So we replace f with what it's equal to, 0.0001 x squared plus 3, and we do the same thing with g of x. So we would get the square root of 120 minus x. So that's our formula for f and g. And I messed up my color scheme. You guys don't have to change anything, but I'm going to change my color a little bit. This. All right. So now we want to find the domain. So we need to remind ourselves for what is the domain of f? Well, the domain of a polynomial is going to be all real numbers. So its domain would be from negative infinity to positive infinity. And now we need to find the domain of g. But when we have a square root, well, what kind of numbers are we allowed to take the square root of? Well, the square root of a positive number is also a real number. So the stuff inside the radical has to be positive. So the radicand, so 120 minus x, has to be greater than or equal to 0. So we add x, and that gives us 120 is greater than or equal to x, or turning it around the other way, x has to be less than 120. So that's going to be my domain of g. H is made by combining f and g. So it's going to be the and of those two things. So if we're trying to find the domain of h, let's visualize it in terms of the domain of f. Well, the domain of f is everything. So if you visualize that on the number line, you would shade everything from positive infinity to negative infinity. For our domain of g, x has to be less than or equal to 120. So we would go to the number 120, and then it has to be less than, so we would shade everything to the left. Well, where those two domains overlap, that's where both functions make sense. That's called the and, or the intersection, is going to be the domain of h, because h was made of f and g. So the inputs have to work in both f and g. So where those two domains overlap, the green, the and, is going to be the domain of h. But we have to be a little bit careful, because there's one more thing. What's the one number we're never allowed to divide by? 0, right? We were doing division in this problem. So we were dividing by g. Is there an input x that has an output of 0? Said another way, what x would I have to put into g to get 0 out? Well, if I put in 120 for x, what's 120 minus 120? 0. So we can't have that as well. So we must exclude x equals 120 because g of 120 is equal to 0. And we can't divide by 0. So then our domain would be from negative infinity up to 120, but not including it. So we put it in a rounded parenthesis instead of a square bracket. So when we have functions or rules being combined, the domain is always the and, or where the two domains overlap. And then if you have division, you have to remove any points where you may be dividing by the number 0. All right, so the last part says calculate h of 116. Well, this is, we're just going to put 116 into our function. So that is 0.0001 times 116 squared plus 3 over the square root of 116. Oh, I'm doing that in the wrong order. 120 minus 116. 120 minus 116. And that's really just calculator food at this point. So let's put those values into our calculator and see what we get. We have 0.0001 times 116 squared plus 3. And then we want to divide that by the square root of 120 over 116. And we get this as our value. Right. Let's take a look at example number 2. So this should really say a right triangle. So a right triangle has an area of 100 square meters. Find its perimeter in terms of x. So I'm going to draw a picture of my right triangle. And I know that its area is 100 square meters. So our area formula for a triangle is 1/2 its base times its height. So if I call this my base and this my height, it wants me to find its perimeter in terms of x. So I'm going to let my base be x then, because it told us to use this parameter. So I'm just going to define my base to be x. Then I know that my area is 100 square meters is equal to 1/2 my base, which is x, times my height. So I can solve this equation for my unknown h. So the first thing I would do is multiply by 2, and that gives me 200 is equal to x times h. I divide by x, and I divide by x, and that gives me h is the same as 200 divided by x. So then we would know this side is 200 divided by x. So now we need to find the perimeter of this triangle. So the perimeter is like the distance around, right? So this side would be x, this side would be h. How do you find the third side of a right triangle? Yeah, the Pythagorean theorem. A squared plus b squared equals c squared. So we can find this missing piece by using the Pythagorean theorem. We know c squared is equal to the two sides squared. So let's use each of our values that we have. So it's going to be equal to x squared plus 200 over x squared. Well, 200 over x, quantity squared. So then, multiplying that out, we get c squared is equal to x squared plus 200 times 200 is a 4 with 4 zeros, all over x squared. So to solve for x, we take our square root, and we get c is equal to x squared, missing a square there, plus 40,000 over x squared. So now we've found all three parts of our triangle in terms of our variable x. So to find the perimeter, what do? We add up all three sides. So the perimeter is the sum of all the sides. So P would be equal to our first side, which is x, plus our second side, which is 200 over x, plus our third side, hypotenuse that we just found, which is this. And that would be the perimeter of that triangle that has an area of 100 square meters. And that would tell us its perimeter in terms of the length of one of its sides. So we came up with a model to tell us the perimeter as a function of one of its side lengths. So let's kind of recap what we did. So it's always a good idea to draw a diagram. We labeled one of our sides as x. We then used the area formula to help us solve for one of the other sides. Then we needed to know the third side, or the hypotenuse, for which we used the Pythagorean theorem to find. And then we just added up the length of all three sides to find the perimeter, because the perimeter is the distance around an object. All right, so now let's move away from geometric problems so much and start talking a bit about models that we'll see in business. So when we're talking about modeling, cost is often something that we wish to talk about. So we have a fixed cost, we have a variable cost, and a total cost. Oftentimes when we're talking about total cost, we'll just say cost. But we want to talk about fixed cost and variable cost. So when we're comparing this to a linear equation, so for linear equations, we have y equals mx plus b. That's our standard equation of a line. In this model, y is the total cost. Mx is the variable cost. And b is the fixed cost. So in general, we have the equation total cost is equal to the variable cost plus the fixed cost. When an equation is linear, our variable cost is going to have the form m times x, where m is the slope, but m is also the marginal cost, like we were talking about in chapter 15. So the slope, that's why the derivative told us what the marginal cost was. The marginal cost is the slope of the variable cost. So this guy right here in the linear model is the marginal cost. All right, so let's use this and take a look at example number 3. A factory produces E272 laptops, computers, and it costs $14,250 each day to operate the factory. The cost to make each E271 is $125. Find the cost function to produce X E271s per day. What is the cost to manufacture 75 E271s? So in terms of our model here, we want to come up with our total cost. And our total cost is our variable cost plus our fixed cost. And our goal is to find the total cost per day, right? So which of those costs is fixed for each day? Well, our fixed cost is going to be the $14,250, because that's what it costs to open the factory each day, just to run it, right? Whether you make 1 laptop or 100 laptops, that's what you have to pay just to get the factory up and running. So then we also have another cost that is associated with it, which is it costs $125 to make each laptop, right? So in this case, it's going to be a linear model, because if it's $125 per laptop, that's going to be our marginal cost. Is $125, so then the variable cost is going to be 125 times x. So 125 is the slope of our line times x, where x is the number of E271s. So then putting all of that into our equation, the total cost as a function of the number of laptops, x, is going to be 125x plus 14,250. So now we can use our model to determine, well, what is the cost to manufacture 75 E271s? So we put that in, and we simplify. So I'm going to push the y equals on my calculator and put this function in. So 125x plus 14250. So the next part asks us to graph it, but I'm going to do that in a second. So we do our y equals, we put our function in. So something you may or may not be familiar with on your calculator is using it to evaluate things. And then we press alpha and trace. We select y1, and we can just put the input in that we're trying to find, which is 75. Oh, apparently I didn't press alpha y1. So alpha trace, we choose y1, and then we put in our 75. We press enter, and it gives us 23,625. You'll note if you were to type that out the long way on your calculator, you get exactly the same number, right? It's just using the y equals will be helpful, especially if you have to do multiple function evaluations, right? Because if I had to figure it out at 75, 80, 85, 90, and so forth, I could do so quickly without having to retype as much stuff. So then the last thing it asks us to do is graph. Well, that's the other thing. Since we already put it in y equals, we can just hit our graph key. And our calculator draws a picture, and we can't see anything. The reason for that is, by default, our calculator always looks in a 10 by 10 window. Well, we know that if we make 75 computers, it's going to be $23,625. So we need to change the viewing window on our calculator. So next to our y equals button, we have a window button. We press that. Since we can't manufacture negative laptops, let's make our x min 0. And let's make our x max a little bit larger. We manufactured 75 in the previous one. So to give ourselves a little bit more room, let's put it all the way up to, say, 250. And instead of scaling our axis in ones, let's go ahead and scale our x values in 25. For our y min, let's do 0. For our y max, we can use what we estimated here, 23,625. We're probably going to want it to be bigger than that. So let's go all the way up to about 100,000, and we'll see how that works. That's 10,000, 100,000. And let's change our y scale to, say, 5,000. So when we press graph now, we see what our function looks like. So if you ever are graphing something on your graphing device and you can't see it, it most likely means that you need to adjust your window. If you adjust it and you still don't see what you want, just keep adjusting it until you do. Because a lot of adjusting the window is sometimes just guesswork. You start, and if you get a picture that shows you what you want, you're happy, you stop. If not, press window and keep modifying until you see the picture the way you wish. And so that would be a graph of our function. If you're being asked to graph something, say in WebAssign, I would pick my xmin, my xmax, my ymin, and my ymax to match up the graph that I'm trying to match to. It will make finding those pictures and matching them up a little bit easier. Our profit is equal to our revenue minus our cost. So, a couple of observations we want to make about our profit, our revenue, and our cost. So, we break even, or the break-even point is when profit is equal to 0. So in other words, it would be the equation 0 equals revenue minus cost. And if we add cost to both sides, we would get that our break-even point occurs, as your intuition would tell you, when your cost is equal to your revenue. So if we're ever asked to find the break-even point for something, we would set our profit equal to 0 or set our cost equal to our revenue and solve the resulting equation. Let's take a look at our next example. A drive-in movie theater a drive-in movie theater that can fit 187 cars has an hourly operating cost of $1,475. If they charge each car $12 per hour of movie, find the hourly profit P it earns operating the drive-in as a function of the number of cars C. Specify the domain and what is the least number of passengers, or the least number of cars, to make a profit. Round your solution to the nearest car. All right, so our goal is we want to come up with our model for this. So our revenue versus our cost. So let's start with our cost. So it says that the hourly operating cost is $14.75, and they charge $12 per hour per car per movie. So what is our hourly profit P? So we know that profit is equal to revenue minus cost. So let's find each of these. So the cost to run the movie theater is going to be $14.75, and we have $12 per hour of movie. So let's go with our revenue as well. So our cost in this case is going to be $14.75, and that's just our hourly operating cost. So that's going to be a constant. And if they change, or if they charge $12 per car per hour of movie, that one is going to be per car. We're going to have 12 times x, where x is the number of cars. So then our profit P is going to be our revenue minus our cost. So our revenue is 12x, take away our cost, which is $14.75. Gives us this. So now we need to specify our domain and what is the least number of cars to make a profit. Well, our domain is going to be the set of values that make sense. So what is the least number of cars that they could possibly have at the drive-in. Well, if they were having the worst business day ever, they would open up and nobody would come to the theater, right? So that would be 0. And then the last part is, well, what's the maximum that they can fit? 187. So that's going to be the largest value in the domain. So their domain consists of anywhere from 0 to 187 cars. So now we want to know, well, what is the least number of cars to make a profit? So let's find their break-even point. So break-even is when P is equal to 0. So we have 0 is equal to 12x minus 1475. So we minus 12x, and we minus 12x, and we get negative 12x equals negative 1475. Divide by negative 12, we divide by negative 12, and we get x is equal to negative 1475 over negative 12. We need a fraction, so we go math. We don't want a fraction, we want a decimal. And we get 122.91, but we're talking about cars and we're supposed to round up to the nearest car, because you can't have a fractional car. So for them to break even, they would need to have 123 cars present each hour.
Professor Peterson?
All right, so supply, demand, and equilibrium price. So a demand equation, or the demand function, expresses the demand Q, the number of items demanded, as a function of the unit price P, or the price per item. A supply equation, or a supply function, expresses the supply Q, the number of items a supplier is willing to make available, as a function of unit price P per item. It is usually the case that as demand increases and supply increases as the unit price increases. Demand and supply are said to be in equilibrium when the demand equals supply. The corresponding values of P and Q are called the equilibrium price and the equilibrium demand. So if we look at our graph here, in orange, this represents supply, and in blue, this is representing demand. So our equilibrium price and our equilibrium demand are here, and this is what's referred to as the equilibrium point. So then the coordinate that's down here on our horizontal axis is, since that's price, that's our equilibrium price. And the coordinate on our vertical axis is the equilibrium demand. And so what is it that each of these curves are telling us in the picture? So let's analyze the blue curve first. So the blue curve looks like it has negative slope, and it is moving down as we go from left to right. So that says, as we increase the price of an item, what happens to its demand? It goes down. So the more something costs, the less demand there is going to be for that item. The supply side of the chain, as the price of an object increases, what happens? More suppliers want to make it because it's more it makes more money. So the point where those two things are equal, the demand for an item and a manufacturer wanting to make it are equal, that's our equilibrium point. So that means that there is enough supply to meet the demand and that the price is equitable to everyone involved. So we're looking at our curves in this way. So let's take a look at a couple of examples. This one's actually, it chains, so this example 5 chains into another example. So the demand as measured by total enrollment for private schools in Michigan depends on the tuition cost and can be approximated by Q of P equals 32 plus 2,000 over P, thousand students enrolled, where our domain for P is between 200 and 2,200, and where P is the net tuition cost in dollars. So our question then becomes, well, what is the effect on demand if the tuition cost is increased from 1,000 to 2,000? Okay, so we need to figure out what our demand is. So this really wants us to calculate Q of 1,000. So Q of 1,000 is going to be 32 plus 2,000 divided by our 1,000. We could put this in our calculator, but 2,000 divided by 1,000 is 1, so we get 33. And we need to find our demand then when the tuition cost is increased from 1,000 to 2,000. So,
Excuse me, isn't it equal to 2, right?
oh, to 2, yes. Thank you. And that gives us 34. And we'd have gotten 0 in a second. And we plug in our 2,000. And we get 32 plus 2,000 over, I did it backwards, 2,000 over blue 2,000, and that gives us 32 plus 1, which is 33. So then our change in demand is Q of 2,000 minus Q of 1,000, which is 34 or 33 minus 34, which gives us negative 1. So, and this is measured in thousands. So that would tell us that if they increase the tuition price by $1,000, the demand would decrease by 1,000 students. All right. go to our next example, which is building on this same model. Suppose that private school institutions are willing to create private schools to accommodate Q equals 32 plus 0.002p thousand students, same domain, 200 to 2200, who pay a net tuition of p dollars. What is the equilibrium tuition price at private schools, and approximately how many students will be accommodated at this price? B, what happens if the tuition is higher than the equilibrium tuition, and what happens if it is lower? And estimate the shortage or surplus of openings at private schools if the tuition is $2,000. So let's start with A. So our equilibrium point occurs when profit equals 0, when supply equals demand. So we need to find when does supply equal demand. So we set our equations equal to each other. So we have from the previous problem 32 plus 2000 over p. That was our demand equation, and then our supply equation is given here, which is 32 plus 0.002p. And we need to resolve this equation. So we have a rational equation, so we need to clear our fractions by multiplying by the LCD. The LCD in this case is, we only have one fraction, is just p. So if we multiply we clear the fractions by multiplying by p. We're going to end up with 32 times p plus 2000 over p times p is equal to 32 times p plus 0.002p multiplied by another p. And when we multiply by the least common denominator, the net effect is that all of our fractions should always reduce out. And we get 32p plus 2000 is equal to 32p plus 0.00. I feel like I lost a 0 there. Oh. Nope. Okay. 2, and then p times p is p squared. So now this equation is quadratic. So to solve a quadratic equation, we need to get it set equal to 0. So we would minus 32p minus 32p minus 2000 and minus 2000. So on the left side, those reduce out and those reduce out. Those also reduce out. So we get 0 is equal to 0.002 p squared minus 2,000. So then there's a few different ways that we can do this. We notice that all of the p's reduced out. So we could then use the square root principle. You could use the quadratic formula, and if you really want to, you could also try to factor it. All of those methods would work. But since we have no p term, just a p squared, we can use the square root principle, which will be the easiest. So we add 2,000 to both sides. I know it seems like we're going backwards. 0.002 p squared. And then we divide by 0.002 and divide by 0.002. So we have 2,000 divided by 0.002. And we get 1,000,000 is equal to p squared. And we take our square root. So square root, second, our negative key down here to pull up our answer from the previous line. And we get 1,000. So we get p is equal to 1,000. So we get that our equilibrium price is p equals 1,000. So now we could calculate the supply and the demand by using this p-value in each of the equations that was given. And we know that they should be the same, so if we use Q equals 32 plus 0.002p, so we go Q of 1,000 is equal to 32 plus 0.002 times 1,000. We get 32 plus 2, which gives us 34. So it would be, and this is measured once again in thousands, so it would be 34,000 students. All right, so now let's back up a little bit. When we started with this original thing right here, let's hit our graphing calculator. Let's graph each of these on our graphing device. So we have 32 plus 0.002. Our calculator doesn't know p's, so we'll put in x. And then we also had 32 plus, we have our fraction, 2,000 over p. And we already know the answer because we solved it is at 1,000, so that's going to help inform me what this is going to look like. So now I press window. Let's make my x min 0, and let's make my x max, say, 3,000. That doesn't divide very nicely, so let's do 2,000, and then we'll do our x scale in hundreds, and then we'll make our y min, let's go 0 to 50, and let's make our y scale 2.5. and we graph, and we get something that looks like this. And I don't like that picture, so let's make our y min a little bit bigger. Let's make our y min, say, 30 to 50, and then let's change our scale to 2. It'll make our picture look a little better. So we get something that looks like this. So we have our demand curve, and we have our supply curve, and then we have our equilibrium point, right? So we found our points of intersection down here, and we can see it in our graph. So how can we use our graphing device to help us find that? So if we go second trace, and we want to find, under second trace, we're looking for the intersection of those two curves. So we choose choice number 5. Since there are only 2 curves in, you can just press enter, 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 and it should work. And where does it tell us the intersection point is? 1034. Oh, those are the same 2 answers we got by resolving the equation algebraically, right? So, as we saw earlier, our equilibrium occurs just like it did in this picture. Our equilibrium point is here with our price and our demand here, and we can find those coordinates by solving algebraically or finding them as we did here. And we have the 34, and once again, that's in thousands. All right. So now, what would happen, so for part B, what happens if the tuition is higher than the equilibrium tuition? And what happens if it is lower? So let's analyze this picture again. Once again, I still don't like that window. So I need to make my x min a little smaller. So I'm going to go back down to 20, and I'll leave it at 2's. All right, so we get something that looks like this. So what's going to happen if the tuition is higher than the equilibrium tuition? And what happens if it is lower? So what is that going to tell us? So if we analyze, remember, we have our price on the horizontal, and we have our demand on the vertical. So if that's the case, here's our equilibrium point. So our price is going to be down here. So what happens if we start moving this way? Well, what does your intuition tell you is going to happen? So if we have a price that is larger than the equilibrium, what's going to happen to the demand? Is it going to go up or is it going to go down? It's going to go down, right? So demand goes down, but what happens to the supply? It's going to go up, because they're going to want to have more people if they can charge more, but then if people aren't interested in going, that's a problem, right? Because they're charging more than the consumer is willing to pay for said product. So if we went and took a look, so we have each of our curves in here. So y2, which is the 32, or y1, the 32 plus 0.002 is our supply, and y2 is our demand. We can evaluate each of these and actually see what the difference is. So if we go alpha trace and we move to the right a little bit. So we had up here, what did we get for P? 1,000. So let's move our P to 2,000. And then we do the same thing. Oh, not with Y1 though. We want Y2 this time. So we have our supply and our demand. So if our tuition goes up to $2,000, they want to make room for 36,000 students, but how many students would be willing to go? 33,000, right? So this is actually going to be useful for the answer for part C. And so we have part C says, estimate the shortage or surplus of openings at private schools if the tuition is $2,000. Well, that is the difference of these two things. So 36 minus 33 would give us our difference. So it's going to be 3,000 seats. And it's worth noting you can do Y1 of 2,000. You can do it all in the same line. Alpha trace, get your Y2 of the same value. And it will tell us that the surplus is going to be 3, and it's measured in 1,000 seats. So the surplus is 3,000 seats. All right, so that